Hello and welcome to the channel. In today's video we're going to be looking at this card here, the Diamond Monster 3D from 1997. It's based on 3DFX's Voodoo graphics chipset, which set the world of PC gaming on fire when it was released. You see, it was one of the earliest 3D hardware offerings directly aimed at PC gamers. It was efficient, it was affordable, and it was compelling. In fact, it was top dog for a number of years. If you want to know more about the history of the development of this chipset and see some of the early tech demos that 3DFX themselves released to show off its features, then check out the video I made recently on the channel. But in today's video, I want to get to the bottom of what this card can actually do at a hardware level, cut through some of the marketing hype and jargon. And unfortunately, I can't program the card at the register level. That would be much too involved for a single YouTube video, maybe a year's work. But I can do the next best thing. You see, I found this fantastic website with all the early 3DFX documentation and the software development kits they released for their chipsets. They developed this graphics API called Glide, which I'm going to be using to program the card. Glide is a little bit like OpenGL or DirectX, but those are much more sophisticated and high level. For example, in OpenGL you can set up a number of lights and use a bunch of different lighting effects. You can do all sorts of texturing effects. It's got everything you need for rotating 3D scenes, setting up cameras, and so on. But Glide is much more linked to the hardware itself. The basic rule of thumb is that unless there's a register in the hardware for doing it, there isn't a function in the Glide interface for it. And actually the hardware doesn't really do all that much when it boils down to it. It can draw triangles, put textures on those triangles, do some very basic shading called Guro shading, and some effects like fog and so on. So that's a little bit of an oversimplification, but I'm going to go through exactly what the card is capable of in this video. I'm going to code up some little demonstrations by coding my way through the interface, and that should give us a really good idea of why this card was so fantastic in the mid-1990s. The easiest way to get started with 3DFX programming is with the Glide programming manual, which sort of goes through everything from the very basics. You do need to know how to program, but for example, here's a minimum Glide program, and it's really quite straightforward. So I'm not going to show you how to program this card because that would be too involved for a video, but I'm just going to go through and point out a couple of things with this minimal example. So first of all, you just start up the Glide library and then you check whether there's any 3DFX hardware, and if not, then you print an error message. And then you select the first 3DFX card in the machine. Now I only have one 3DFX card, so this will be card number 0. And then we have to open a window, and this is what really starts up the 3DFX hardware and gets it ready for drawing stuff on the screen. So we select the resolution and the refresh rate that we want and the pixel format, which in my case would just be RGB alpha. And you can also change whether you want the origin in the lower left of the screen. And this number here is the number of buffers. So I'm going to use double buffering, so this will be a 2. And the advantage of double buffering is you can render in one buffer while the other buffer is being displayed on the screen. And then you won't get any ugly artifacts while you're drawing your objects that you want to display. And then this one here is the number of auxiliary buffers, and you'd set that to 1, for example, if you wanted a depth buffer for 3D stuff. Anyway, then you just have your program for displaying your points and lines and triangles and so on. And when you're done, you just call Glide Shutdown. So it's really straightforward and it's explained quite well in the manual. Now in the previous video I set up the Whatcom-C compiler so we could compile the tests which come with the Glide distribution. And I'm just going to modify one of these, test 00, by adding progressively more features to show off what the card can do. But let's start with something basic. We'll just draw some points on the screen and move them about. Now interestingly enough, points are actually implemented in hardware using little triangles because that's actually all the hardware can do. And what I'm doing here is plotting points by using the cosine and sine functions to give the coordinates of points on a circle. And in a moment I'm going to start rotating the circle, And this is done by updating the offset to those functions every frame and redrawing all the points every frame. Now all of this is done using double buffering. I have two buffers, one which I clear and update, while the other buffer is displayed on the screen. Once I've finished updating a buffer, then I switch the buffers so it becomes the one that's displayed. And of course this happens very, very rapidly, giving you the appearance of animation. Now it's not quite circular here because the pixels in this mode aren't quite square, but you get the basic idea. And now in a moment what's going to happen is anti-aliasing is going to be switched on. It doesn't really do very much for points, it just makes them a little larger. In fact, it just draws 4 pixels per point instead of 1. But for lines, anti-aliasing is a big deal. It's used to get rid of jaggies in straight lines, and so it's a really important technique in computer graphics. Anti-aliasing is actually explained quite well in the Glide manual. This is what we'd really like when we're drawing a straight line on the screen, but if these squares represent individual pixels on the screen, we certainly can't have part of a pixel white and the rest black. Instead, we'd have to fill the entire pixel in black, and this would give a kind of jagged appearance to the edge of the line. So instead, with anti-aliasing, what we do is we fill the pixel with a color which represents how much of the line that pixel overlaps. So these light pixels here only just touch the line tangentially on the very edge. These dark pixels are really right over the middle of the line. Now up close it doesn't look very good, but from a distance, because the pixels are really small on the screen, this can look really smooth in comparison to just filling the pixels in all one color. Now of course the next thing to do is straight lines. And I'm using the same animation with points going around a circle, but I'm drawing lines between a given point and some point a few steps along, and just changing the number of steps as the animation goes. And this gives a kind of iris effect, which grows and then shrinks. Now in a moment it'll switch over to anti-aliasing, so you should see the jagged lines that we have at the moment become a little bit thicker, but also a little bit smoother. So it's switching over now, and it'll take a while before we can see some lines, but you can certainly see that everything's much chunkier now, and it's a little bit harder to see any jaggedness on these lines. They look really smooth, and that's the idea behind anti-aliasing. Well, it wouldn't be much of a 3D card if it didn't draw triangles, and that's what I'm using here to draw this rotating tetrahedron. But the card isn't actually doing very much here. It's just drawing triangles and removing triangles that are facing away from the camera, so-called backface culling. But everything else I'm doing myself. I put the coordinates for the tetrahedron into my program, and I wrote the code for rotating those points using rotation matrices. I just take those rotated coordinates and I just feed them to Glide to draw on the screen as 2D triangles. Yeah, 2D triangles. I'm not even using the third dimension at the moment. In fact, if a triangle had a higher Z value, in other words it moved away from the viewer into the screen, it actually wouldn't get smaller at the moment. So we really need to fix this. For the tetrahedron it doesn't matter too much, but this cube looks completely whacked out without perspective correction. The back of the cube actually looks bigger than the front of the cube because things are not getting smaller as they move away from the camera. By the way, I'm using the polygon feature of Glide here, in this case 4-sided polygons for the faces of the cube. And the card itself doesn't actually have the ability to draw polygons other than triangles. So Glide actually breaks convex polygons of any number of sides up into triangles to pass out to the card to be drawn. Well, here's the same cube with appropriate perspective correction applied, and it does look a whole heap better. You might imagine that all I did here was pass the Z coordinates to Glide and let it sort out the perspective. But that's not actually how this works. In fact, if you pass Z coordinates to Glide, it pretty much just ignores them, unless you're doing Z buffering, which I'll talk about a little bit later. And the philosophy here seems to be that only high complexity operations, per pixel operations across the faces of the object, get done by the card. Things like texture mapping and lighting, for example. And per vertex operations, things like rotation and perspective correction, get done by you on the CPU. So there's an interesting division of labour between what gets done on the graphics card and what gets done by the processor in the machine. Well, everything's been fine and dandy until now, and that's because we've been using convex objects like the cube that didn't have any holes or indents in it. But as soon as we do something like this cube with a hole right through the middle, then things begin to mess up. And this is because the polygons that are facing towards the camera are not blocking polygons that are further away from the camera. They need to be drawn last so that they cover up the other polygons. But that's not happening here. And that's because the card has no idea which order the polygons should be drawn in. Now, we could get around this by sorting the polygons, but we'd have to do that sort every single time we draw a frame. And that would get very expensive, especially since you end up breaking up polygons into much smaller ones in order to do it. So the other way around this is something called a Z buffer. And what it does is it records a Z coordinate for every point on the screen. And you just draw polygons in any order you want, and it'll only change the color of a point if the new point has a Z coordinate that's closer to the camera than what's already been drawn. So this is something the card can actually do automatically for us. We can use one of the auxiliary buffers as a Z buffer and fix this problem. So let's turn Z buffering on. Well, after 5 extra lines of code, it looks great. And can you imagine trying to implement Z buffering yourself and making it efficient? That'd be a big job, but this was no sweat at all. Now, if you thought something else looked wrong in that previous clip, one of the polygons in the center of the cube actually had the wrong orientation. If you specify the points in the wrong order, then it thinks that the polygon's facing away from you whenever it's actually facing towards you, and so it'll get removed at the wrong time. So I fixed that and it looks fantastic. But how is this Z buffering actually implemented in hardware? Well, it turns out that you don't specify Z coordinates for each vertex, but 1 on Z. And furthermore, you scale the values so that they give you an integer from 0 to 65,535. So it's a 16-bit approximation to the 1 on Z value. Then the card uses this and interpolates across the face of each polygon that it's painting and figures out the 1 on Z value for each pixel. Now that sounds very precise, but it's only a 16-bit approximation, and it can happen that 2 points which have different Z values can map to the same 16-bit integer when you do this transformation. And that can cause artifacts. So for this card, they actually invented a new technique called W buffering, which gives a kind of floating point approximation to something that matches more the concept of the distance to the camera. And this actually gets rid of all of the artifacts that you would get from naive Z buffering. Can you see what's different this time? Obviously I've got lighting going on, and in fact I have a light source set up at infinity, and I'm varying the color of a face depending on how much it's pointing towards or away from the light. And this is called flat shading. All of the pixels on a face are the same color as one another, but that color is changing over time depending on which way the face is pointing. But we can actually do better than that with this card. We can use Guro shading, and this is useful for when you have a light source up close to the object and you want to simulate the effect of the pixels changing color as you move across the face depending on which direction the light source is from that particular position. There's 2 ways of doing this. You could use Phong shading, which is very expensive, and so this card can't actually do that. That's where you recompute the lighting value for each pixel as you move across the face from scratch. But instead of doing that, the card does Guro shading, which is much cheaper. This is where you just specify the lighting value at the vertices of each face, and that's the programmer's job. It's not a function of the card. And then you just leave the card to interpolate between those values. So in other words, it does a gradient across the face which matches up with the pixel colors that you specify at the corners. Now, it doesn't look that much different from flat shading. I've slowed it down here so it's a little bit more obvious, and especially when the face is sort of turned side on, you can really see the gradient, or perhaps if you stop the video you'll see it more easily. So it does work, and it's a really nice feature of the card. Well, I'm pretty happy with where things have got to so far. It's not too bad for a weekend of programming, but it is pretty tiring, and I think the video is going to be a little bit too long if I just keep going. We're only about halfway. There's all sorts of things left like texture mapping and various lighting effects. And we could even do fog and make a little video game environment that we can move about in. And maybe you guys have some suggestions as well. If so, put them in the comments below. I'd really like to hear about that. So obviously there's going to be a second part to this video, and that'll be coming up in the coming weeks. So if you enjoyed this video so far, don't forget to like this one and to subscribe to the channel so that you get informed when the next one pops up. I'm also a little bit conscious of the fact that I have some travel to Australia coming up, and I need to allow time to edit all the videos, otherwise there'll just be nothing while I'm away. So maybe I better focus on some slightly shorter videos, or at least ones that are easier to edit over the coming weeks. Anyway, for today, that's it, and thanks very much for watching, and we'll see you in the next video. Bye!